All right, let's just dive right into this. Welcome to today's explainer. We're basically undertaking an absolute masterclass on the real engineering, the strict definitions, and the global standards behind high-speed travel. I mean, if you've ever watched a bullet train just slice through the landscape and wondered how it all actually works behind the scenes, you are absolutely in the right place. So I want to start off by posing a really fundamental question to you. What exactly makes a train, quote-unquote, high speed? I think our immediate instinct is just to say, well, it's a train with a really powerful engine that goes super fast, right? But as we're going to see today, in the world of railway engineering, simply pushing a locomotive to its absolute limits on standard everyday tracks is literally a recipe for disaster. It's not just about the vehicle itself. It's about something much, much more comprehensive. And the formal definition beautifully illustrates the real answer here. High speed isn't a single thing. It is a completely integrated system. It's this uncompromising combination of three critical elements. You've got the infrastructure, which means the tracks, the curves, and the power supply. Then there's the rolling stock, which is the train itself. And finally, the operating conditions, like the signaling and the safety rules. You cannot have true high-speed rail without all three of these pillars perfectly synced up. It is not just a fast vehicle, it's a fast environment. Okay, here is our roadmap for the explainer today. 1. Welcome to High Speed 101. 2. The UIC high-speed definition. 3. Upgraded versus new lines. 4. High-speed system selection. And 5. Why the system matters.
All right, Section 2, the UIC high-speed definition, setting the global standard.
So the UIC, which is the International Union of Railways, they are the governing body that coordinates high-speed activities across the globe. Just think about it. If every single country built their tracks, their trains, and their computer systems entirely differently, you could never have a train travel seamlessly from France into Germany or Spain. The UIC's primary job is to harmonize technical standards so that this massive, incredibly complex global network can actually communicate and function as one unified whole.
Now, the UIC makes this really clear two-tier distinction when defining high-speed infrastructure. And this is totally crucial for our focus today. High speed isn't just one magic number. According to the UIC, there are specially built lines, which are brand new tracks engineered right from the ground up for speeds generally equal to or greater than 250 kilometers per hour. But then there are specially upgraded lines. These are pre-existing conventional tracks that have been meticulously retrofitted to safely handle speeds of around 200 kilometers per hour. So high speed fundamentally depends on whether the earth beneath the tracks was freshly carved out for 250 plus or smartly adapted for 200.
Moving into Section 3, upgraded versus new lines, the engineering reality. Remember earlier when we said high speed is an integrated system? Well, here are the 5 state-of-the-art components that have to be flawlessly calibrated to meet those UIC speeds. You need the infrastructure we just talked about. You need the rolling stock. You need incredibly strict operational rules. You need advanced signaling systems, mostly because human eyes literally cannot process track signals fast enough at 250 kilometers per hour. And you even need targeted marketing to make sure the immense costs are actually economically viable. If even one of these components fails to match the line's designated speed, the whole shebang breaks down. So the absolute key here is compatibility, right? The design of the train, the rolling stock, has to perfectly guarantee safe, uninterrupted travel at 250 kilometers per hour or more when it's zooming along those brand new lines. But because these networks are all interconnected, that very same train must be able to seamlessly adapt its performance down to the 200 kilometer per hour limit when it transitions onto those specially upgraded tracks. It really is a marvel of adaptive engineering. Let's actually think about a practical example of that 200 kilometer per hour upgraded definition in action. Sweden realized their population density just didn't financially justify laying thousands of miles of brand new 250 kilometer per hour track, so they opted to upgrade their existing lines instead. To safely hit that 200 kilometer per hour UIC threshold on older, curvier tracks, without completely throwing passengers out of their seats, they use tilt body technology. The train literally leans into the curves. It's a brilliant, highly cost-effective way to achieve high-speed status by mastering the interaction between the rolling stock and the upgraded infrastructure.
All right, Section 4, high-speed system selection, types of networks.
Take the Japanese Shinkansen. This is what's known as a Type 1 system, and it is the absolute purest form of high-speed rail. In a Type 1 system, you have a completely exclusive, dedicated network of brand new lines. The high-speed trains only run on these specific tracks, and absolutely no other type of train, no slow local commuters, definitely no heavy freight, is ever allowed on them. It is 100% segregated. Now contrast that pure Type 1 system with a Type 3 mixed system, like the Spanish AVE network.
In a Type 3 system, those brand new high-speed lines are shared. So they're used by the ultra-fast 250-plus trains, but they also allow certain conventional trains to hop on the tracks, often using some really cool special gauge-changing technology. However, mixing these different types of trains invariably leads to capacity reductions, simply because you have to so carefully manage the crazy speed differences between them.
Which brings up a really massive engineering dilemma. Why do engineers overwhelmingly prefer those exclusive Type 1 lines if they can afford them? Well, there are two major reasons derived from European studies. First up, speed conflicts. If you put one very high-speed train on a track, it eats up so much schedule space that it disrupts the path of 3 or more slower goods trains. But second, and honestly way more critically, heavy freight trains literally destroy the track's microgeometry. We're talking about the millimeter-perfect alignments required to keep a fast train stable. If you run heavy freight overnight, the track geometry deteriorates so much that it becomes physically impossible to safely run a passenger train at 250 kilometers per hour the next morning. Segregation is the ultimate key to sustainable speed.
Section 5. Why the system matters. Safety, capacity, and the future.
Back in 2014, test speeds hit some absolutely astonishing numbers. We're talking France at 574.8 kilometers per hour, Japan at 581, and Germany and Spain both clearing 400. Now, while these are definitely isolated test speeds and not commercial everyday speeds, they prove a really critical point. Because these countries rigorously follow the UIC's integrated system approach, the engineering tolerance of their networks is just incredibly high. Everyday commercial speeds of 250 or 300 kilometers per hour are actually well within the safety margins of what this infrastructure can handle. And that rigorous engineering leads directly to an absolutely crucial fact. High-speed rail is statistically one of the safest forms of transport in the world. Often, it's safer than conventional, slower rail. Why? Because the system demands it. There are no level crossings where you might hit a car, the advanced computer signaling systems, the moving block cab signaling, and continuous speed control make the risk of collision exceedingly low. The system will automatically slam on the brakes if a driver ignores a speed limit. It is a total myth that at high speeds, trains just randomly fly off the tracks. The physics and the computer oversight simply do not allow it. Because of this unmatched blend of speed, incredible safety, and massive passenger capacity, and remember, a dedicated high-speed line can increase transportation capacity 5-fold, the societal impact is just profound. I want to share this quote directly from the source material. It is likely as the high-speed rail grows in Europe, flying around will become a way of the past. Think about it. When you can travel city to city in under 3 hours, straight to the downtown core, totally bypassing airport security lines, the entire calculus of travel fundamentally shifts. Which leaves us with this final thought. We've seen how the strict definition of high speed, whether that's building brand new for 250 kilometers per hour or brilliantly upgrading for 200, creates an astoundingly safe and efficient system. So, as this complex engineering marvel continues to expand across the globe, overcoming all sorts of topographical and financial hurdles, it begs the question, are we looking at the technology that will finally ground short-haul commercial air travel for good? It's a fascinating engineering reality to consider the next time you look at a map. Thanks so much for joining me on this deep dive.